So on that take home, you have a derive the moment of inertia problem. This is like what we did with we did a bar that rotated about an axis through its center. This is the same derivation except we're going to have it rotate around an axis at its end. So it's like a broom handle going around and around, but from the end, not from the middle. And that's going to change the moment of inertia. It'll increase its moment of inertia because it has more mass at larger radii. It'll largely, you're going to work it in the same way. It's going to change your limits of integration though, so it'll change the final answer that you get. You can probably find it online, maybe, I'm not sure. This isn't really usually the way that we derive for a bar, uh, but I think that you can figure it out. It's largely just changing your limits of integration, okay, guys? And then we're going to get into this today or Friday where we do statics, and so there are two static problems. If you want to work on it over the break, that's fine. If not, that's fine too. We'll get, oh no, we're not here next week, are we? Friday's beginning, or the last day of class. We'll get into this. It's stuff that we've seen before, so we're not going to spend a lot of time on it. Mostly we're going to work through problems. We'll work through 4 different scenarios, and just to help you get the technique of working through these static problems, because it's nothing new. Some of the forces equal 0, some of the torques equal 0. Mostly it's just how do you approach it mathematically, and how do you look at a physical situation. So there are 2 problems that are static problems. We'll work through some similar ones in class today and then on Friday and then on into next week. And then next week we're going to get into optics. We'll probably spend a couple days on optics. And then after that week on Monday we'll have the exam. All right. Uh, and then as I told you, the final is cumulative. So if you want to start preparing for the final, it probably wouldn't be unwise to start preparing for the final just to start jogging your memory on exams 1 through 3. If you're preparing for the final, only look at the exams that we've worked this semester because material that's not on our exams won't be on the final. So if there's a topic I left off one of our exams, you won't see that on the final. So when you go back to other old exams and practice those, you might encounter stuff that you won't see on the final. I'm not saying that you disregard those old exams because they can be useful just to practice, but just be aware that if it's not on our 4 exams, then it won't be on the final. In fact, I'll go through our 4 exams and I'll just pull questions from them. That's how I make the final exam, and then I'll change them in various ways. We'll talk more about that as we get closer to the final. Any questions about the take home, which is for exam 4? It's worth 30 points, so not insignificant. Hopefully that's 30 points that everybody gets completely. Uh, and then also remember with take homes, I expect I have a higher bar, so I don't give as much partial credit. So please, please, please make sure that you get the right answer. But then also, I'll expect to see your work. You can use any resource. You can work together. I encourage you to work together, in fact. If nothing else, just to check your work against one another, even if like the day before you turn it in. If you get stuck, you can come see me, and I can push you in the right direction. But I'm not going to show you how to work it. Any questions about the take home? What to expect? We'll turn it in on the day of the exam 4. So you have plenty of time, but you know, you have lots of other stuff going on too. Any questions about the final? No? All right. Well, if you do, let me know. Um, I think we are on angular momentum. So let's do a few clicker questions first. Where did we leave off? We did some of these, right? Yeah, y'all remember where we left off? I'm not sure if we got up to the angular momentum question or not. Yeah, I know we did this one, but how far did we get, y'all? You might know on the clicker questions. Oh, you have them up? You oh, yeah, I know. I'm sorry. But what was the last one that we did? You don't know? Do you know? Oh, there's just one left? Oh, okay. All right. Well, we'll hold off then on these. Because we need to cover momentum. Wait, did we cover momentum? We did cover momentum, right? Angular momentum? Okay, so let's just do that last question then. I didn't realize we got so far. We did this one, right? Did this one? No? Alright, let's try this one out. Oh shoot. Let me pull up my clip and paste. Okay, while I'm waiting for that, I want to tell you about something else. Let me blank this, and we'll do that. There is a research opportunity. I really recommend that you guys take advantage of. This is, I think that y'all, as students, you should have received this email about the SULI program. Can y'all see that? One, yeah. Kim, you can see. What this is it's a research program where you go to a DOE lab. So like that would be Los Alamos, Oak Ridge up in Tennessee, out in California. There are a couple of labs around the country. There are DOE labs, Department of Energy labs. These labs, and historically, they were tasked with uh, supporting our nuclear arsenal, but now their research is widely varied. When I was an undergrad, I did a 9-month program at Los Alamos, and it really helped me to figure out what it was that I wanted to do and gave me a lot of experience working with scientists and with these various projects. And it just really helped me as a student to solidify the direction that I wanted to go into. And also, it paid pretty darn well. I mean, I paid, I think, I don't know, 7, 8, 9,000 for the summer. I mean, they included your housing and a stipend and all that business in there, and it's a lot of fun. You work, you get an advisor that mentors you. You know, you don't take classes or anything. You just go to work every day and you work on various projects. So it's a fun thing to do. They pay you pretty decently, better than working at Canes for the summer, and it's good experience. So I really encourage y'all to apply for these. I'll actually send this notice out to y'all on Moodle, but the application is there. I think it's due. I don't think it's due. Oh yeah, it's due in January. So you have time over the break to work for it. And if you need recommendation letters, let me know. I can write you a letter for this. A really great opportunity, really help you to form an idea about what you want to do in the future. And you know, if that's not what you want to do, that's fine. Just go do it and have a good time. And it's good experience regardless for whatever you want to do. They have all different fields. They have physics and astronomy, of course, but then they have biology, chemistry, material science, engineering, all sorts of different work that go on at our nation's labs. Lots of fun for you to do. I really encourage that you do so. All right. They pay housing and travel too, and you get to hang out with students for the summer. You know, they usually put you in like an apartment building with all the other research students. Okay. Pull this back up. Okay. So a figure skater spins with her arms extended. When she pulls in her arms, she reduces her rotational inertia because she no longer has mass at big radii, and her moment she spins faster so that her angular momentum is conserved compared to her rotational energy. After she pulls in her arms, her rotational kinetic energy must be what? Is it hot in here? How warm? A little bit. I'm going to open this back door. I think they turned the heat on. So when she pulls her arms in, one, her rotational inertia gets smaller, and her rotational speed goes up. And so both of those things, kinetic energy is dependent upon both of those things. We want to know which of these has the greater effect, or do they cancel one another out? All right, we'll stop in about 8 seconds. I'll stop at 133. So we're sort of split here. A couple different things are happening here. So I know that L is equal to I omega. And when she brings her arms in, her rotational inertia decreases. So I goes down by some amount. Let's say down by, say, a factor of a half. That means that omega is going to go up by the same amount, say by a factor of a half, because they're directly related, right? If I goes down by a certain amount, omega has to go up by the same amount. And then our rotational kinetic energy is 1 half I omega squared. Now notice here, if we have the same thing, where I goes down by a factor of a half, then omega goes up by a factor of 2. But which of those is going to dominate in the kinetic energy? Is the kinetic energy going to increase or decrease? I have a factor of a half here, and then I have a factor of 2, but this omega is squared, so this increases my kinetic energy by a factor of 4. This is going to take it down by a factor of 2, and the overall net result will be to increase the kinetic energy by a factor of 2. So B is the right answer here. Even though the rotational inertia decreases, the angular velocity increases, and the kinetic energy is more dependent upon the angular velocity because it's squared than the rotational inertia. Where does that energy come from? Y'all come on in. Sorry, I just put that there for the cross ventilation. If you could pull it back into the door, Ashley, or somebody. Thank you, Jean. Oh, no, keep the door propped open. I just walked past it. Where does that energy come from? Because, you're probably thinking right now, wait a minute, she just changed her rotational inertia, and then all of a sudden she has more energy, right? That's what you're thinking? And you're thinking, what's up with the conservation of energy, right? Where did that energy come from? Where did the energy come from? She increased her rotational kinetic energy, so where did that energy come from? She had to have done work, right, in order to increase her energy. And what was the work that she did? The slide on by, Tyler. Well, she does work, right? What is work? It's a force times the displacement. What is the force that she does when she changes her rotational inertia? What force does she exert? And over what displacement does she exert it? Right. Have y'all ever tried to move into a merry-go-round, to move from the outer edge into the middle when it's spinning? Have y'all ever done that? It's not easy though, right? Somebody's done this, right? On a merry-go-round, it spins around, you try to move in. It's not easy. You have to exert a force over a certain displacement. And similarly, she has to do the same. When she pulls in her arms as she's spinning, it takes a lot of force, and then that causes her rotational kinetic energy to increase. All right, two different spinning disks have the same angular momentum, but disk 1 has more kinetic energy than disk 2. Which one has the bigger moment of inertia? So L1 is equal to L2. They have the same angular momentum, but disk 1 has more kinetic energy than disk 2. Which one has the bigger moment of inertia? This goes back to the previous question a little bit. All right, I'm going to stop at 115. 115. We're sort of split up on what we think the answer is. All right, so A and B got sort of equal things. Which one of these is spinning faster? The one with more kinetic energy or the one with less kinetic energy? Which one do you think is spinning faster? Disk 1 or disk 2? Disk 1, right, because kinetic energy is 1 half I omega squared, And omega, the kinetic energy, is more sensitive to the omega because of that quadratic term, because omega is squared. And so disk 1 is going to be spinning faster than disk 2. But if L1 is equal to L2, what does that say about the moment of inertia of disk 1? If omega 1 is big, what does that tell us about I1? Is it big or small? It's going to be small. So the moment of inertia of disk 1 will be smaller than the moment of inertia of disk 2. And this question is asking which has the bigger moment of inertia, and so that would be disk 2. So the key idea here is that the kinetic energy is more dependent upon the angular speed, the angular velocity, but the angular momentum, there's an inverse relationship. If I goes up, omega goes down by the same amount. You can see similar questions on the test in the multiple choice part. So I would go through and sort of review these questions and think about those different relationships. I like those type of questions, those relationship type problems. All right, we had a question similar to this back in chapter 5, or 6 rather, on our momentum chapter. What do you think about it? Ask your neighbor what they think. All right, I'll stop at 115, 115. Okay, good. A is right. You remember the similar problem that we had in chapter 6? It was a train car that was moving along the tracks and it rained into it, and we said that it slowed down because momentum was conserved. That means that its momentum remained the same. When you increase the mass, then the speed had to go down. The same thing is true here, that uh, as it rains into these buckets, the masses of the buckets increase. That means that the moment of inertia increases, but the momentum has to remain the same, and so the speed goes down. As I goes up, the speed goes down. And what kind of songs do the planets sing? Neptunes. Okay, let's go on to chapter 9. You'll want to look at the homework for chapter 8. Be working on those. Think about the different types of questions. As I said, you're going to see a Newton's second law thing. You'll probably see an angular momentum thing. You're going to have to do a cross product. Um, work through the homework. Look at the old test, okay? All right, let's look at chapter 9. Chapter 9 is entirely going to be on the take home. Okay, and in chapter 9, as I said, we're going to have very little new stuff here. In fact, no new stuff here. The only thing that we need to know is that in equilibrium problems, all bodies are static. That means they're not moving. And because of this, these two criteria are met. Now, we've already seen this. The sum of the forces equals 0. And we worked through that in chapter 4, where we had forces. We had to add up the forces in the x direction, and those were equal to 0. The sum of the forces in the y direction, that was equal to 0. And then we're also going to say that the sum of the torques is equal to 0. And we've seen this too, sort of. We did a very simple statics problem with the seesaw thing. Those are statics problems. And like in the lab, when you did the meter stick with the masses on them, that's a statics problem. But now we're going to combine these two ideas and use them to solve for more complex situations. Because this gives us a whole new thing in our arsenal. You know, the sum of the forces equals 0. That really only produces just two equations. But the sum of the torques equals 0 adds at least a third equation to our mix, so we can now solve for three unknowns. But then we'll see that we can also add a fourth and a fifth and any number of equations simply by changing our axis of rotation. So when solving these problems, one must often determine the center of mass for objects. And don't worry, on the objects that we'll be dealing with, the center of mass will be obvious. It'll be at the center. Like with our meter stick, the center of mass was at 50 centimeters. And then we're also to select a point of rotation that will eliminate unknown variables. So you remember we had a couple points where our, never mind, we'll come back to that. I'll show you what this means. Let's just work through some examples. We'll work through 4 examples today and on Friday, and maybe on into after the break. But I think in working through those examples, it'll give you an idea of what to do for the take-home. The take-home is similar to some of these, and the take-home is even a little easier than some of these. But you might want to go ahead and print out that take-home, and as we're going through the examples, think about how you would work the take-home problems, because some of them are very similar to this one. I'm going to skip example 1 because I think example 1 is a little more difficult, and we'll go straight to example 2. But we'll come back to example 1. All right, so here I have a bar. It says it has a mass of 100 kilograms, has a length of 10 meters, and the center of gravity, or the center of mass, is at its midpoint. It's suspended by 2 cables, and there's a mass hanging 3 meters from the end of the bar. What is the tension in each cable, and what is the angle theta? So here I have 3 unknowns. I want to know what is this tension, what is this tension, and then I also want to know what is this angle theta. The first step in working these is drawing all the forces that are at work and labeling any distances. So what are the forces that I have acting on this object, on this system? Let's see, I can think of 1, 2, 3, 4 forces that are at work. Can you identify the 4 forces? Okay, we have a tension and we have a tension. That's 2 of them. But then we have 2 more forces. Okay, we have what weight? There's no normal force because there's no surface here. Remember, a normal force is the surface pushing on the object. But you're on the right track, Dustin. What do you think? The weight, or gravity is a weight, and so what is it the weight of? Okay, we have the weight of the bar, and then we have the weight of the mass. All right, so we have 2 tensions, the weight of the bar and the weight of the mass. We dealt with the weight of the bar in the lab with the meter sticks. When you move the axis of rotation over out of the center of mass and you had to account for the weight of the meter stick, it's a similar thing here. So I'm going to draw all these forces. I have this one. Let's see, I called this one FTL for the left tension. And then I have this one over here. I call this one FTR. Do you know what the R stands for? Right, right, yeah, it stands for right. And then I also have this one. I just called this F, and then I have the weight of the bar, which I call FW. Now I also need to list distances because we're going to be measuring torques, and when we measure our torques, we need to know the distance from the force to the axis of rotation. So let's just sort of label these distances. I know that the length of the bar is 10 meters, and so I can say, well, this distance must be then 5 meters. It tells me in the problem that this distance is 3 meters from the left of the bar. And then that leaves me with this distance, which is 7 meters. All right, I can draw all of my forces now. Do the sum of the forces in the x and the sum of the forces in the y. what we're going to do is we'll collapse all these forces down to a central coordinate system. So we can draw a coordinate system that'll look like this. You might not need to do this, but I'm going to do it off here to the side. Like if you can see this, that's okay. Here's my FTR. My FTL is over here. This is theta. This is 60 degrees. And then I have two an F, and an FW right here. I can find the X and Y components. Let's see, I'll do them in magenta. Right here, this is FTL cosine theta. This is FTL sine theta. And then I have FTR sine theta, or excuse me, sine of 60, and FTR cosine of 60. So all I did is I wrote down all the vectors that I have, and then I resolved FTL and FTR into its X and Y components, because those aren't on axis, and so you'll need to resolve them. And you'll encounter similar questions. In fact, there was a very similar question to this in the on the take-home that you'll see. It's a little bit different, but similar. So now I write some of the forces in the X and the Y. Some of the forces in the X is just going to be FTR cosine 60 minus FTL cosine theta. That's equal to 0. And then some of the forces in the Y is FTR sine 60 plus FTL sine theta minus F minus FW, and that's equal to 0. Let's think about what our unknowns are here. Because I have two independent equations, two equations that don't depend upon one another, and the unknowns include FTR, theta, and FTL. And I have a similar number of unknowns in the second equation. I have FTR, FTL, and sine of theta. Is it possible to solve this system of two equations for three unknowns? Is that possible? Not possible. In order to solve a system of equations, it can have no more than the number of equations and unknowns. So if I have two equations, I can only have two unknowns. If I have three equations, I can have three unknowns. If I have four equations, I can have four unknowns. And if I have a million equations, then I can have a million unknowns. And I can solve for those million unknowns. And that's where that whole that matrix method that some of y'all did on the previous exam, that's where that comes in useful, because then you can actually solve a million equations for a million unknowns. You chemists, you engineers, sometimes you might encounter a million unknowns, and whether you're building a big building or a bridge or whatever, you have all sorts of forces that are at work, or if you're modeling the interactions of gas molecules, you have, billions or trillions of molecules or more, lots of molecules that are interacting with one another. But if you can write an equation for each of those unknowns, then you can solve them. So I have a problem here because I have three unknowns but only two equations. And I need to figure out some other equation. And that's where we're going to use that, that second criteria, which is that the sum of the torques is equal to 0. So right now you're thinking, well, in previous problems, when we had the sum of the torques, I had the axis of rotation labeled. But here, we don't have an axis of rotation. In fact, this thing is static. And so the question is, where is the axis of rotation? And often that's going to be the hardest part in these problems, is figuring out where is the axis of rotation. So look at this figure and think about, where is the axis of rotation? This figure that is in a static situation, it's not moving, not rotating, where is the axis of rotation? And we could think of several things, right? We could do the axis of rotation maybe at the center of mass. That might be okay. We could do the axis of rotation down here. Is it going to rotate about this end? No, it's not going to rotate at all. So when you're thinking on these static problems, Don't think of, well, where does it rotate around? You want to think of it mathematically and think, what axis of rotation gives me the best advantage in solving this problem? That is, which axis of rotation removes the most number of variables? Remember, there are two ways that forces can apply no torque. Y'all remember the two ways? Like if you think about the door, one of the ways is that if the force acts parallel to the moment arm, no force. So it's like trying to open the door by pushing in this direction. And the other way that a force applies no torque is by pushing on the axis of rotation. So any force or any variable that's at play at your axis of rotation is not going to be in your equation because it's not going to provide a torque. So if you're looking for an axis of rotation that removes the largest number of unknown variables, then in this problem, where would you put your axis of rotation? You want it to be in such a place where it removes the biggest number of unknown variables. So for example, you're not going to put it right here because I know exactly what F is. I know that F is 100 newtons, 10 times G, which is 100. Likewise, I'm not going to put it here because I know the mass of the bar. Where would I put it? I'd put it over here, right, because I know neither theta nor do I know FTL. So let's see what happens when I put my axis of rotation right here. I can say that the sum of the torques equals 0, and I'm going to say the sum of the torques on the left end with our axis of rotation on the left end. I can say that the sum of the torques equals 0, and then I do just like we've been doing. I say that, let's see, the torque due to this one is negative, this torque is also negative, and this torque is positive, because they're clockwise, clockwise, counterclockwise. So that's equal to F times 3 meters, or excuse me, minus F times 3 meters, minus FW times 5 meters, plus FTR sine of 60 times 10 meters. And that this is all equal to 0. So now I have 3 equations and 3 unknowns, and I can solve this. And it actually is not that hard to solve, because if you notice, how many unknowns do I have in this last equation? I only have one unknown. So I can easily solve this for FTR. Let's run through that right quick. So F is 100, so this is minus 300 minus, the bar has a mass of 100 kilograms, so FW is 1,000 newtons, so this is minus 5,000 Newton meters, plus FTR, sine of 60 a half, I always forget, I think it is, no, so it's 8.6 times FTR. All right, and then I can solve that for FTR equals 5,300 divided by 8.6. And that is 616 newtons. Make sure that's right. Yeah, 616 newtons. All right, now that you know FTR, you can plug it in up here, and now we have a system of 2 equations with only 2 unknowns, and you can substitute one equation into the other. I'm not going to do that here, but I'm just going to write it in words here. Now you solve this system of equations by substitution. On your take home, you'll have a very similar procedure. You'll need to figure out, where do I put my axis of rotation? And most of the time it's going to be where you have the most number of unknown variables. It doesn't make any sense to put it any other place except where it takes away unknown variables. I could put it here, but it doesn't make any sense to do that. I could say this is my axis of rotation. I could put it here, or anywhere along the bar. That allows me, by the way, to set up all new systems of equations by putting my axis of rotation at various points. But it doesn't make sense mathematically to do so. It only makes sense to put it where you have unknown variables. So I could write an equation for my axis of rotation here, or down here, or any other place. But the most advantageous place is to put it right here. Okie dokie. So that's going to be your general procedure. You'll you're going to have three sets of equations. Usually one of those you can solve because it only has one unknown variable, and then the other two you have to solve by substitution. We're going to work through some more examples, but right now we need to pause because we're going to do evals this week. Uh, so I need somebody that's willing to take the evals to the dean's office. The dean's office is right over in Pelcher Hall. You just need to put them in the envelope. Jesse, you got it? Thank you. So give me just a moment. I want to tell you a little bit about the evals. At Nichols, we have two sets of things, and both of them are very useful to me. And since I'll see many of you next semester, because you take two semesters, it's helpful for you to spend a little bit of time on both of these. The first thing is this form. If you need a pencil, let me know. I have some pencils. Anybody need a pencil, a number 2 pencil, or a pencil? All right, I'll leave you one. If you could just leave it up here on the desk when you're done, because that's a chemistry pencil. Anybody else need a pencil? All right, so this is the SIR form. This goes away and it goes into the administrative system, and they record your responses. And at the end of the semester, after the grades roll in, I get a form that says, well, this is how you scored in this particular area. And I always compare it to sort of see how it compared to previous semesters. It helps me to think about how the class is going. So please read the questions and then answer accordingly to how you feel that question, you should respond to it. So if you pass those out, Jake, the CCN number, which you'll need for that form, is 81331. Now there's another part. Jake, you have the free response problem. Oh, we have a new form for this. This is the open comments. And on the open comments, this goes sealed away into an envelope and nobody sees it except for me. So I always use this form. I usually make one or two changes in the course. I really appreciate critical feedback, anything that worked, anything that didn't work. If you could think about that on this form. If you want to use expletives or draw a picture, that's fine. I'm the only one that sees it. I'm not easily offended. So this is for your open comments just between you and me. It's anonymous. And so whatever you write here, I'll read it, but I won't know that it's you. Do you mind handing these up? All right. Let me get out of here. They say we're not supposed to be around while y'all are writing these, but it's going to take me just a couple minutes to get everything shut down.